Hello everyone. Today we're going to be solving an indefinite integral. It's going to be the first integral we're going to solve on this channel. So that's pretty cool. So let's look at it. We got, let's see, the integral of the square root of x times the cube root of x times the fourth root of x times the fifth root of x times the sixth root of x, on and on and on and on till infinity dx. Okay. So we got an infinite chain of of roots inside roots inside roots. How do we solve this? Well, the first thing we can do is we can simplify this mess right here. This mess can definitely be simplified a lot. Because if we try to use, let's say, u substitution here, how would that even be possible? You got an infinite number of x's. You can't take the u substitution and wipe away all of them. So there has to be a better algebraic way to start this problem, at least. Well, we can do this. What's this right here? Let's write it again. The integral of, well, this is the square root of x. So we got x to the power of 1/2. What about this x? Well, yeah, it's the cube root of x, but it's also the square root of x. It's a cube root inside a square root. So what it is x to the power of 1/2 because it's square rooted, but it's also cube rooted. So we multiply by 1/3. Now let's do it again. So x to the power of 1/2 times x to the power of 1/2 times 1/3 times x to the power of 1/2 times 1/3 times 1/4, because the fourth root is inside the third root is inside the second root. So you got 1/2 times 1/3 times 1/4. And I think you can see where this is going. Let's just do one more. Times x to the power of, well, we got the fifth, it's inside a fifth root, but that fifth root is inside a fourth root, which is inside a third root, which is inside a second root. So it's just 1/2 times 1/3 times 1/4, 1/4 times 1/5, and then times so on, dx. Okay. So we have this kind of weird pattern over here. So that's good that we got that. But how does that help us? Well, actually, it does help us in this. We can even simplify this. We don't have to say 1/2 times 1/3, 1/2 times 1/3 times 1/4. So we could say the integral of x to the power of 1/2 factorial, right? 2 factorial is just 2, so nothing too interesting there. But the next one, you can do x to the power of 1/3 factorial. Then we can go plus x to the power of 1/4 factorial plus times x. Didn't mean plus. I meant times x. So x to the power of 1/2 factorial times x to the power of 1/3 factorial times x to the power of 1/4 factorial, and so on and so forth till infinity dx. So remember, factorial, so the factorial of 3 is 3 times 2 times 1. The factorial of 4 is 4 times 3 times 2 times 1. So, and remember, that times 1 isn't really needed. So if we have a 1/2 times 1/3, well, that's just 1/3 factorial. It's 1/3 times 2 times 1. And same for 4, 5, 6, on and on till infinity. So, what can we do after? Well, we know that rule of exponents where we can add them together if the base is the same. So you can do the integral of x to the power of 1/2 factorial plus 1/3 factorial plus 1/4 factorial, on and on and on, dx. Okay, we got that. Now what? We simplified it as much as it can. We can't do really any other algebra tricks here. So what do we do now? Well, we can do this. We can recognize that this is a pattern very reminiscent of the Taylor series for E. Now, if you don't know, E can be approximated as, well, in fact, it actually is not just approximated, 1/0 factorial plus 1/1 factorial plus 1/2 factorial plus 1/3 factorial, and so on and so forth till infinity. That infinite sum is the same thing as e. It's exactly e. So we can use that to our advantage over here, right? Now, I will say I won't go into why this Taylor series is equal to e, but there are a lot of other videos that you can look at on the power series of e, the Taylor series of e. So you can look at that on your own time if you'd like. Well, what do we have here? We have 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. On and on and on. So we almost have this series over here. This is almost this, except for the 1 over 0 factorial, which is just 1, and the 1 over 1 factorial. However, 1 over 0 factorial is 1, 1 over 1 factorial is 1. So this is e equals 1 plus 1, so 2. E equals 2 plus 1 over 2 factorial plus 1 over 3 factorial. So if we take the 2 to the other side, we get e minus 2 equals 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, on and on and on. And now we can substitute. This right here, 1 over 2 factorial plus 1 over 3 factorial, on and on, is the same thing as over here. 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, like that. So let's substitute. We got the integral of x to the power of e minus 2 dx. And now it's just a simple power rule. We got e minus 2. If we want to integrate it, we have to raise the power and then divide it by that power. So we have to raise the power by 1 and then divide it by that new power. So we get x to the power of e minus 2 plus 1 is e minus 1. And we have to divide it by e minus 1 again. And don't forget the plus c, the constant. This is an indefinite integral, meaning we need the constant over here. So this is our final answer. We got x to the power of e minus 1 divided by e minus 1 plus c. And that is the answer to this pretty crazy looking integral right here. All you had to do was know some little patterns and some algebraic manipulation.